blue to red, blue white line కనిపిస్తుంది. ఇది వాటర్ కనిపిస్తుంది. మీరు ఒకసారి క్లాస్ చూసుకోండి, ఒకసారి అదే బాగా కనిపిస్తుంది. చూసుకోండి 9:50 నేను చూసుకుంటున్నాను. చూసుకుంటాను. Good morning, students. Now we go through the wave optics from interference. In wave optics, interference. See, before the interference, first you should know principle of superposition. Principle of superposition. Principle of superposition in the sense, if you consider two or more waves traveling in the same direction, combined with one another, then the resultant displacement is equal to the vector sum of displacement of individual waves. Suppose it is a wave with a displacement y1. This is another wave with a displacement y2. These two waves traveling in the same direction, after certain distance, if they combine with each other, then you will get a new wave. That new wave have a displacement y is equal to y1 plus y2. Y is the resultant displacement. Y1, Y2 displacements of the waves. This is called as what? Principle of superposition. Principle of superposition in the sense, if two or more waves traveling in the same direction combined with one another, then resultant displacement is equal to the vector sum of, because displacement is a vector sum of individual displacements. This is what? Principle of superposition. Now, interference. What is interference? Interference in the sense, interfere means combining. If you consider two coherent waves having same frequency, traveling in the same direction, then the resultant intensity will be changes regularly. Changes means becomes maximum, becomes a minimum. That means the variation in the resultant intensity, due to, here I am writing, the variation in the resultant intensity, due to the superposition, of two waves. The variation in the resultant intensity due to the superposition of two waves is nothing but called as interference. Superposition. Superposition means what? Combining with each other. Whatever the number of waves you can take, that is 2, 3, 4, or anything you can take, any number of waves we can consider to get superposition. Now, in this interference, variation in the intensity, resultant intensity, variation in the sense, at some points you will get maximum intensity, at some points you will get minimum intensity. Wherever you get the maximum intensity, their brightness is more. Wherever intensity is minimum, their darkness is far. That means, if we consider, suppose, if we consider two light waves traveling in the same direction, combined with each other, then wherever they combine, at some points, maximum intensity means brightness. At some points, minimum intensity means darkness. That means, see here, it is the screen. It is the screen. Here I have taken a one more cardboard sheet which is having two small holes, narrow holes. Here, yes is a source of light which can produce the light. Now, when the light coming from S moving towards the cardboard sheet having two holes, very narrow holes, small holes. Now, one wave coming through this hole, one more light wave coming through this hole. If these two waves combined at any point on the screen, at this point darkness may be formed or brightness may be formed. Suppose at this point one wave coming from this hole reaches, one more wave coming from this hole reaches this point. I am taking P and Q. These are, you may taken as S1 and S2. That means slit S1, slit S2. Slit in the sense narrow hole, like suppose if it is a paper, in this paper make a small hole like this in the shape of rectangle, that is can be called as a slit. That means, now in interference, the variation in the resultant intensity due to the superposition of two waves. Here, one light wave coming from upper hole, another wave coming from lower hole. They are combining, they are moving in the same direction, combined at point P. This is what we are assuming screen. Now, whenever the two light waves coming from two holes and interfere means combining at point P. At this point P, we may observe either darkness or brightness. Suppose at this point again, coming from S1, coming from S2, combine at this point, you may get again either brightness or darkness. That means suppose here brightness, darkness. That means what? Intensity is what? Varies, variation, changes, brightness, darkness. This formation of brightness and darkness on the screen due to the combination of two waves is called interference. Interference means, remember, formation of brightness and darkness, due to the superposition of two light waves. Now, to get this interference, we should consider coherent waves only. I think it is over. Coherent waves. What are coherent waves? The waves, those are having same frequency and having zero phase difference or constant phase difference. See, coherent waves in the sense the waves those are having same frequency and constant phase difference or zero phase difference. Coherent waves having same frequency and constant phase difference. They have to maintain constant phase difference. That means, see, here we are taking two holes from S1, one wave is coming from S2, one wave is coming. At the point at the beginning, if these two waves are having a phase difference of 30 degrees, at each and every point they must maintain phase difference how much? 30 degrees only. At this point, phase difference between the two waves is 30 degrees. At each and every point in their path, they must have phase difference how much? 30 degrees. And their frequencies are also must be equal. Then only they are called as what? Coherent waves. Coherent waves means waves those are having same frequency and a constant phase difference or zero phase difference also you can take. Zero phase means what? Here both the waves having same phase. Suppose phase difference in the sense what? Say, suppose light wave displacement denoted by y1 is equal to a sin omega t. Y2 is equal to a2 sin omega t. I am assuming this is the displacement of first wave. This is the displacement of second wave. Y1, Y2 are displacements. A2 are their amplitudes. Amplitude in the sense maximum displacement. Omega t phase angle of the first wave. Omega t phase angle of the second wave. Now phase difference in the sense what? Difference in their phase angles. Phase difference means difference in their phase angles. Phase angle of first wave omega t. Phase angle of second wave omega t minus omega t is equal to what? Phase difference may be denoted by phi. Phi is equal to what? 0 degrees. That means coherent waves must have zero phase difference or constant phase difference. Constant phase difference. Here difference of these two angles is 30. At each and every point they must have 30 degrees. Suppose at the beginning if they have phase difference is 0, at each and every point they must have 0 phase. That's why say constant phase difference. Now they are called what? Coherent waves. Coherent waves. How we can get coherent waves? From coherent sources. Coherent sources of light. What are the coherent sources of light? The sources of light which can produce the light waves with the same frequency and the constant phase difference. Or simply we can say coherent sources are the sources of light which can produce coherent waves. Example. Source of a light and its virtual image or virtual source. So example this one. Here S is what? Real source of light. That means you can put an electric bulb or lamp, anything. If it is electric bulb, from this electric bulb we have taken a cardboard sheet. For the cardboard sheet we made small holes. Now the light produced by this bulb coming from S reaches the hole S1 and S2. Through these holes light will be passes. And whatever the light waves coming from S1, whatever the light coming from S2, these two S1 and S2 acts as what? Coherent sources. Here S1, S2 will be taken as coherent sources. Why? Because the light wave coming from S1, light wave coming from S2, having same frequency. having same frequency. How we can say light waves coming from S1 and S2 having same frequency? That means from S1 and S2, how the light is coming? From S. Here S is what? An electric bulb. From this electric bulb, light is passes through S1 and S2. That's why light waves coming from S1 and S2 having the same frequency. And automatically they will maintain the constant phase difference. Example, source of a light and its virtual source. That means S is a real source of light, and here we have taken one cardboard sheet. From this one, a hole is made. Now light wave coming from S, number of light waves, because a source of light can produce the light in all directions uniformly. The light wave coming from S passes through this hole. And light wave coming from this hole. This is the first wave, this is the second wave. These two light waves having same frequency and a constant phase difference. Now here yes, and if it is this hole is denoted as S1. Now S and S1 taken as what? Coherent sources, because they are producing coherent waves. Frequency and a constant phase difference. How we can produce coherent waves? From coherent sources of light. For this, coherent waves, due to the superposition principle, already it is over. Resultant amplitude A is equal to, you will get formula root over A1 square plus A2 square plus 2A1 A2 cos phi. A is what? Resultant amplitude of two waves, when two waves combined with each other. Two waves combined with each other. Resultant amplitude formula root over A1 square plus A2 square plus 2A1 A2 cos phi. A1 A2 are what? Amplitudes of two individual waves. Phi is what? Phase difference between the two waves. And intensity is always directly proportional to square of the amplitude. I proportional to A square. Therefore, squaring on both sides, what you will get? A square. Square root gets eliminated. A1 square plus A2 square plus 2A1 A2 cos phi. Now, I proportional to A square. A square in the sense I is equal to A1 square means what I can write? I1. Plus A2 square. A2 square means you can write I2 plus 2 into here I proportional to A square. Taking square root on both sides, root I proportional to what you will get? A. That means here A proportional to root I. Then A1 proportional to root I1. A2 means what? What I can write? Root I2 into cos phi. Formulas for resultant amplitude and resultant intensity due to the combination of two coherent waves formula. Resultant amplitude, resultant intensity. This resultant intensity becomes maximum and minimum, becomes maximum and minimum due to the combination. When these two coherent waves combined with each other, resultant intensity will be changes. Changes in the sense maximum, minimum, maximum, minimum. These two formulas. When you will get maximum, when you will get minimum, that is depends on the phase difference, because when angle changes, cos value is also changes. Cos value changes in the sense I is also changes. Now we will come to the interference. This interference pattern explained by Young. Scientist name is Young. He has conducted one experiment to prove to observe the interference. That is, we can call as Young's double slit experiment. Simply we can call as YDSA. Young's double slit experiment. Young's double slit experiment explains about the interference pattern. Explains about the interference pattern. YDS, Young's double slit experiment. Okay. Before going to this YDS experiment, interference is of two types, you can say. Constructive interference, destructive interference. See here. First one is constructive interference. Second one is destructive interference. Constructive interference in the sense, assume you can assume brightness. Destructive interference in the sense you can assume darkness. See, constructive interference, destructive interference. Constructive interference in the sense, in the region of interference, if the crest of one wave falls on the crest of another wave, light waves are example for transverse waves. Here, light waves are example for transverse wave. Transverse wave, how we can draw it like this. In this transverse wave, upper portion is called crest and the lower portion is called trough. And when you will get constructive interference, this is the first wave. And one more second wave is also like this. See, these two are combined. How they are combined? Crest of the first wave falls on the crest of the second wave, or trough of the first wave falls on the trough of the second wave. Then you will get a constructive interference. There you can observe brightness, or we can say if the two waves having the same phase, or you can say in phase, same phase. See, remember, same phase in the sense what? Physically, what is the meaning of same phase? Same phase in the sense, the two waves must reach the higher value at the same time and reach the lower value at the same time. That means, see here, x-axis, along x-axis time, along y-axis, suppose along x-axis anything you can take at time, it is position. Now, see here, at this time, both the waves having the maximum value. At this time, both the waves having minimum value. Maximum, minimum, maximum, minimum. That means they reach their maximum and minimum at the same time. Now they are said to be in phase or same phase. See, constructive interference. When you will get constructive interference, when two light waves traveling in the same direction combined, how they should combine? Crest of the first wave falls on the crest of second wave, or trough of the first wave falls on the trough of second wave, or they must have same phase. Or in phase. Same phase in the sense, phase difference between them must be is equal to 0 degrees. Then you will get constructive interference. Constructive interference in the sense, brightness will be observed. That is constructive interference. Second one, destructive interference. Destructive interference in the sense, in the region of interference, the two light waves must undergo in opposite phase. Opposite phase in the sense, crest of the first wave falls on the trough of second wave. That means, see here, this is the first wave I am taking, and this is the second wave I am taking. This is the second wave. How they are combined? Crest of the first wave falls on the trough of second wave, or trough of the second wave falls on the crest of first wave. That means like this. And they must have opposite phase. How we can say opposite phase? Along x-axis, if you have taken time t. At a particular time, first wave reaches the maximum, second wave reaches the minimum. Say above x-axis maximum, below x-axis minimum. At a particular time, first wave reaches the maximum, second wave reaches minimum. Next, again after a certain time, suppose 0, it is 10, it is what 20. After 10 seconds, first wave reaches maximum, second wave reaches minimum. After 20 seconds, second wave reaches maximum, first wave reaches minimum. That means at any time they must have opposite phase. Opposite phase. Opposite phase means phase difference must be is equal to what? 180 degrees. Now this is called as what? Destructive interference. Destructive interference in the sense, in the region of interference, the two light waves must undergo opposite phase. Opposite phase in the sense, crest of the first wave falls on the trough of second wave. Now they will have a phase difference of 180 degrees. Now there you can observe a darkness. Darkness means no light is observed. No light is observed on the screen. This is the two types of interference. Constructive interference means brightness. Destructive interference means darkness. For these two types of interference, we will give some conditions. That conditions will be given in YDSC experiment. Young's double slit experiment. In this Young's double slit experiment, first we should take a real source of light S and keep your cardboard sheet from S at equal distances. Made two holes. They are called slits also. Hole in the sense circular shape, slit in the sense rectangular, narrow rectangular shape. And it is S1. It is S2. And S1, S2 must be at the same distance from S. S1, S2 must be at the same distance from S. Then only they will produce, S1 and S2 can produce coherent waves. S is the real source. S1, S2 are what? Virtual sources of light. Why we are calling S1, S2 virtual sources means light is not coming from S1, S2 originally. Light is coming from originally from where? Yes. Here S is the real source of light and S1, S2 is what? Virtual sources of light. When S1, S2 are the same distance from S, then only they can produce the coherent waves. Coherent waves means we did already. What it is? The waves having same frequency and maintain constant phase difference. Constant phase difference at any time. Now S1, S2 becomes a coherent waves because due to the combination of coherent waves only you will observe interference pattern. Due to superposition of incoherent waves. Two types of waves we are saying. Coherent waves, incoherent waves. Coherent waves can produce interference pattern. Incoherent waves never produce interference pattern. Incoherent waves in the sense their phase difference never be a constant. Phase difference changes randomly. From time to time their phase difference changes. At the beginning phase difference between the two waves 30, next maybe 35, next 40, 45, 25 like that. From point to point phase difference changes, then that two waves are called incoherent waves. To observe the interference pattern, we must consider coherent views. Next, put a screen. This is the screen. S is the real source of light. S1, S2 is what? Virtual sources. And the distance between S1 and S2 taken as always small d. Small d in the sense in the YDAC experiment formulas. Remember, small d in the sense distance between the slits. Slit in the sense narrow rectangular hole. And distance between slits and screen is always denoted by capital D. Distance between slits and screen always denoted by capital D. And when you are taking a point on the screen, that is exactly opposite to the midpoint of S1 and S2. This point always denotes bright, always bright, always bright. See, on the screen where you will get brightness always, that means at a point on the screen exactly opposite to midpoint of S1 and S2. How? You will get always a brightness, bright band or bright fringe at O in the sense. See, the light produced by the source of light, yes, travels in all directions. The light wave reaches S1, one more light wave reaches S2, and they are coming through these holes. Suppose I am assuming these two light waves combined at point O like this. You may represent with the straight lines or in the waveform also. The waves coming from S1 and S2 superimposed at point O. Now what I am saying, at O, brightness is always found. Brightness is always found because one relation is the relation between phase difference and path difference. Phase difference phi is equal to 2 pi by lambda into delta x. Relation between phase difference and path difference. Phi is what? Phase difference. 2 pi by lambda into delta x. Lambda is the wavelength. 2x delta x is the path difference. Path difference in the sense of difference of their length, path length, difference of their path length. This is the path. Measure this path length, measure this path length. Suppose path length of the first one is if we got 3 meters, path length of the second one is if we got 4 meters, difference their path lengths. 4 meter minus 3 meter is equal to what you will get? 1. 1 is what here? Path difference. Path difference in the sense difference of their path lengths. Now, 4 meter minus 3 meter is equal to 1 meter. 1 meter is what? Path difference of these two waves. Now, phi is equal to 2 pi by lambda into delta x. Now, we can observe here, O is what? Exactly opposite to the midpoint. When O is the exactly opposite to midpoint of S1 and S2, then automatically the path lengths of first one and path length of second one compulsory equal, because you can measure length of this line and length of this line automatically becomes equal. When path lengths are equal, phase difference becomes 0. Phi is equal to 2 pi by lambda into delta x in the sense path difference. Path difference means that path lengths are equal at point O. Now, into 0. 0 tending is 0. When phase difference is 0, automatically you will get a brightness. One condition is there, brightness. To get the bright band, what is the phase difference between the two waves? In that condition, if you got a phase difference is 0, then you will get brightness. See, that's why on the screen at a point exactly opposite to midpoint of S1 and S2, always you will get a brightness. That's why this point is called central bright fringe. Central bright fringe. Instead of fringe, you may call it as band. Bright band or dark band. Bright fringe or dark fringe. Now, you can take any other point. Suppose here I have taken a point P. Now the wave coming from S1 reaches the point P. The wave coming from S2 reaches another point P. See, now here the path lengths are not equal. Path length S1P is less and the path length S2P is more. S2P is more. That's why at point P you may get either brightness or darkness. But at point P always you will get brightness because their path lengths are equal. Here path length is not equal. That's why at point P you may get either brightness or darkness. That is, the determination of brightness or darkness at a point on the screen depends on number of waves present in the path difference. See, this point is important. The determination of brightness or darkness at a point on the screen depends on the number of waves present in the path difference. In the path difference. See, when you draw a normal from S1 onto S2P, now almost see length of S1P, and here I am putting a point N. What I did here, I draw a normal from S1 onto the S2P. Now length of S1P, length of NP almost equal. Now this is only extra length traveled by the second wave. This is only extra length traveled by the second wave. And this is only taken as what here? Path difference. This is only taken as path because this path length is less, this path length is more. How much is more in the sense? This one. That's why here S2N is taken as what? Path difference. S2N is called a path difference. Now, here at P, we cannot say whether which one is formed, brightness or darkness. How we can say in the sense, the determination of brightness or darkness at a point on the screen depends on the number of waves present in the path difference. S2N, this is only taken as path difference. In this path difference, how many waves are present? If you know the number of waves in this one, then you can say which one is observed at P, whether brightness or darkness. Now, here I am assuming angle theta. Drawn a line from midpoint of S1 and S2 to the point P. It is also here making an angle theta. Here what condition is there? Capital D must be greater than small d. Capital D must be greater than d, small d. And theta is very small. This angle must be equals to very small, because when d is more than small d, automatically theta becomes very small, very small. Now, to get the brightness and darkness at any point, if path difference is S2N contains an integral number of wavelengths. If S2n contains an integral number of wavelengths, we get bright fringe or brightness or bright band. If S2n contains an integral number of wavelengths, integral number of wavelengths means what? Simply you can write n lambda. N is equal to 1, 2, 3, 4 and so on. Next, if S2n contains an odd ODD, odd number of half wavelengths, then we get dark fringes. Whenever this path difference S2n contains integral number of wavelengths, that means n lambda n is an integer, then you will get at point P bright fringe. If S2n contains odd number of half wavelengths, in the sense S2n is equal to 2n minus 1 into lambda by 2, where n is an integer 1, 2, 3, 4. Put n is equal to 1. Then what you will get? 2 into 1, 2. 2 minus 1, 1. 1 into lambda by 2, lambda by 2. When n is equal to 1, then S2n, what you are getting? Lambda by 2. Put n is equal to 2. 2 into 2, 4. 4 minus 1, 3. Then S2n, what you will get? 3 lambda by 2. Put n is equal to 3. What you will get? 5 lambda by 2. See, 1 into lambda by 2. 3 into lambda by 2. 5 into lambda by 2. Next, what you will get? 7 into lambda by 2. What I said? Odd number of odd 1, 3, 5, 7. Odd number of half wavelengths lambda by 2. Lambda is what? Wavelength. Half wavelength lambda by 2. That means when S2n contains odd number of half wavelengths, that means lambda by 2, 3 lambda by 2, 5 lambda by 2, 7 lambda by 2. Then at point P, you will get a dark fringe. So that means the determination of brightness or darkness at any point on the screen depends on the number of waves or number of wavelengths in path difference S2n. Now, in this YDSAM's demonstrated experiment, you will get formulas for maximum intensity, maximum amplitude, and conditions for bright fringes and conditions for dark fringes. Conditions for bright fringes, conditions for dark fringes. Condition for which value of phase difference you will get bright fringes. For which value of path difference you will get brightness. Same. For which value of phase difference you will get darkness. For which value of path difference you will get darkness. That means you should find path difference and phase difference values for darkness and brightness in this experiment. That is what YDS. In the next class, we can derive the conditions for brightness and darkness in this experiment. After that, we have to go through fringe width also. Here, brightness, darkness, alternative will get it. I said here at point O, if we got bright, that means that bright, if you observe like this in this shape, now it is we can call as what? Bright band. Next, immediately you will get a dark band. This is bright band. This is a dark band. Next, you will get bright. Next, you will get dark. Like this. Next here also, bright in the sense, next one immediately you will get it dark. Next you will get bright. Like this you will get alternatively brightness and darkness in Young's double slit experiment when you consider the coherent waves. When you consider coherent waves, alternatively, this is central bright band. Next it is first dark band D. This is first bright band B. This is second dark band. Central bright band, first dark band, first bright band, second dark band. Next we will get second bright band, third dark band, third bright band. Like this, alternatively you will get brightness and darkness on the screen. How we are getting this alternative brightness and darkness? Due to the superposition of two waves. That is only called as what? Already we said interference. Interference means what? The variation in the resultant intensity due to the superposition of two light waves. Due to the superposition of two light waves traveling in the same direction. This formation of alternative brightness and darkness is called interference. That's why interference pattern is observed and explained by Young's double slit experiment. We can continue in the next class. This Young's double slit experiment.